Hello, everybody. It's Miss Peachy again from your WCA physics class, and we are looking at Unit 4, Lesson 4, Net Force and Free Body Diagrams today. That's what we will be going over. Let's go through those key words, shall we? We have acceleration, we have applied force, gravitational force, free body diagram, friction force, net force, normal force, tension force, unbalanced force, and vectors. So we are talking a lot about forces here, right? So free body diagrams are oftentimes also known as force diagrams. Go figure, right? And they're not too difficult to draw, but the purpose of drawing them is to be able to simplify all the forces that are acting on an object, so it makes it easier for us to understand a complex system. So just like many other different models in science, that's kind of its purpose, is to simplify something that's complicated to make it easier for us to understand and to really assess the different forces that are on the object. All right, so the sum of all forces acting on an object is known as the net force. So when we're looking at these free body diagrams, we are also going to be looking at the net force that's acting on an object. That's kind of the goal in a lot of cases, is to see what the net force is going to be. So if there's um, opposing forces, for example, one of them is going to win that tug of war competition. And the force that wins out is the net force, the one that has the primary um, direction, the one has the greater amount of force, right? You think about with tug of war. You're both pulling in two different directions, but one person wins because they're pulling harder. They have a stronger force, right? Rate of change of velocity is acceleration. We know that unbalanced forces occur when more than one force acts on something in one direction and then in the opposing direction. So again, that example of tug of war. And a free body diagram is kind of breaking this up here. So a couple of things for free body diagrams that are very, very important. First, we represent the object in a free body diagram by a square or a circle, just a simple shape. You don't draw a picture of the object. And then all the forces on that object are drawn outwards from that object. Even if the force is acting on the object and it's pushing, it is we draw it outwards from the object. So, for example, let's see here. The applied force F sub A here, which is an arrow going in this direction. This is representing pushing this box. Obviously, when you push the box, you are going to be pushing it like that, right? But that's not how we draw the arrow indicating that force. They always act outwards from the force. The arrows themselves are drawn proportionately to the magnitude of the force. So the stronger the force is, the longer the arrow is supposed to be. They're not like specifically a certain length. It is a relative length, but the greater the force, the longer the arrow. So that when you're looking at the picture, you have a visual of which force is stronger and which force is weaker. So again, outwards from the box in the direction that force is acting, and then proportional to the magnitude of the force. And then you label them, and the forces are labeled with a capital F for force and a subscript indicating the type of force. So we have a subscript of little f for friction, a subscript of A for the applied force. That's also like your push or your pull, right? If it is tension, we would put a force F sub T. We'll talk about tension in a little bit as well. The force of gravity pulls downward, that's F sub G. And then we have F sub N, and that is our normal force. And that's kind of a tricky force to understand. It's something we don't really think about, but it is actually there. So say I have a book here. And for the teacher, I have an apple sitting on top of the book, right? The apple has weight. The weight is a measure of the force of gravity that's pulling on this apple. We can kind of see this, by the way. If I hold the book is deformed based on the weight of the apple, right? And if I were to put something that doesn't weigh as much as the apple, say this small stone on the book, it does not deform as much because it's not as heavy, right? So the reason why the apple doesn't fall through the book is because while the apple is being pulled down by gravity, the book itself pushes back at the apple with an equal and opposite force. If the forces were unbalanced, then the apple would either fall through or be pushed upwards. So an unbalanced force results in motion that occurs. So whenever we have an unbalanced force, we have a change in the inertia of the apple. And we don't in this case. Think about the first law, Newton's laws. An object in motion tends to stay in motion, and an object at rest will stay at rest unless there's an unbalanced force that is applied to it. So in this case, the force of gravity is pulling it down. The force that is pushing it back upwards, that equal and opposite force, that's Newton's third law, by the way, is the normal force, we call that. And that normal force is really the force that is found like at the atomic level when you're looking at how the molecules are arranged and how they have connections to each other. They actually have bonds, and those bonds, while they might give a little bit at first, kind of deform the shape of the book, they're holding strong and pushing backwards. And sometimes it's that opposing force, that normal force, that gets to be a little bit kind of hard for us to understand because we don't feel a push. We just know we're not falling through, right? So that's our normal force. And the normal force will always oppose gravity, and it will always be equal to the force of gravity, always, okay? So let's look here. Since force is a vector quantity, each force in the free body diagram must be indicated with both a magnitude and direction. Arrows always points in the direction the force is acting, and again, the magnitude is always indicated by the length of the arrow. We also have, we're also giving the magnitude a number as well, right? So most of these, the initial picture is drawn so that we visually see that this is a greater force here, but we also numerically write down the magnitude of 100 newtons. Remember that force is measured in the SI system in newtons. So we have the opposing force. So here, the force of gravity is pulling down with a force of 50 newtons. The normal force pushes back with an equal and opposite force of 50 newtons. So we know those are always balanced. The frictional force is actually opposing the motion of the box with 50 newtons to the left. And the applied force, the box is being pushed 100 newtons to the right. And so we know that the net force in this case is going to be 50 newtons to the right. So it's not just 50 newtons. Remember, it's also we need to have the direction in the rightward direction because a vector has both magnitude and direction. So you can practice a little bit with this, just understanding how to add these vectors together and what the net force is going to be. It's a pretty simple concept. The other force that we didn't mention, but I kind of briefly mentioned earlier, is the force of tension. So, tension is the force that exists on a rope as you pull something, a rope or string or whatever, but it's a tensional force. And tension opposes the weight or the pull of something. And typically, tension is going to be equal to the um, the applied force, right? So if as long as there's no motion occurring, as long as there's no motion occurring, we have tension that is going to be equal to the opposing force. So a tension force exists when ropes and chains and cables are pulled. You cannot push on a rope. If you pull on a rope, however, you will feel tension. The tension is the rope pulling back on you with an equal amount of force. If a rope is under tension, the tension force is the same at all points along the rope. Differing amounts of tension cannot be present in different parts of the rope. When drawing a free body diagram, the designation of F sub t is used to indicate the tension force. A free body diagram involving tension is illustrated below, and we can see here, right? So you're pulling on the rope here in this direction, F sub t, and in this particular case, it is greater than the force of friction, so you're actually pulling it. It's going to move, so it's because it's greater than friction. So we see In the second example, we have a suspended object, an object hanging from a cable. It's not moving, so the force of tension is going to be equal to the force of gravity, equal and opposite. So it's similar in a way to normal force in that it's equal and opposite to gravity, but that's pretty much where the similarities end. It is the tension on the rope as the object is hanging, suspended by a cable. If we were to suspend it by two cables, the tension on both ropes would be the same as the tension as the force of gravity. So the force of gravity here is 1,000 newtons, and we're splitting that force between two ropes. And remember, it's the same in both, so they would be 500 newtons apiece. Okay, so again, pretty simple so far, right? The tricky part comes when we look at forces that are applied at an angle. So when forces are applied at an angle, we need to do a little bit of trigonometry to figure out what the net force is on that particular um, whatever that angle is. So we have to take this angle and we have to break it down into its x and y components. Oh man, did you think we were done with that stuff? We are not done with that stuff. You won't be, because the stuff we need to do. Because in the real world, it's everything isn't going to be perfectly horizontal and perfectly vertical. There are going to be things applied at angles. And so that's what is happening here. So you will see here that you're pulling this rope. Well, this is actually a push, applied force, but you're pushing kind of at an angle here. Potentially, it looks like it's being pulled at an angle, so I would probably call that F sub t because it's tension, right? We just got done saying that. So personally, I'm saying this is F sub t. Doesn't really matter. It's a force applied at an angle, because most of the time when I'm pulling a box, I'm not going to like sit down real low and kind of pull straight horizontally. I'm going to probably be standing up and pulling because that's easier for me to do, right? And so this is our applied force. And what we need to know is we need to figure out the components of that. So we need some numbers here, I believe. Does it give us numbers here? Okay, so it says the applied force is 50 newtons. So I'm going to go ahead and just draw this over here, because I can't copy that. All right, so here is our applied force, and we said that's 50 newtons. And we can break it down into its x component and its y component. If we know the angle here is 45 degrees, and we just need to know x and y, right? Then we can just do a little bit of math. SOHCAHTOA. So sine, cosine, tangent. SOHCAHTOA. Okay. So we have the hypotenuse here, right? If I want to figure out my x component, x is going to be the adjacent. So we're using cosine. So cosine, I'm actually going to scooch this over to give myself just a little more room. Cosine of 45 is equal to x over 50. So if I multiply both sides by 50, cancels out over here, it becomes 50 cosine 45. So on your calculator, you want to put cosine of 45 times 50. In my calculator, I have to hit 45 cosine, and then I have to take times 50. And that gives me a measure of 35.4. That's my x component, right? And my y component is going to be sine of 45. So for the y component, I say sine of 45, because sine is opposite, remember, is equal y over 45, or y over 50. So again, multiply both sides by 50. And I have to figure out 50 sine 45. All right, so sine of 45 times 50. Oh, it's the same. I knew that already. So it's also 35.4. That's not always the case. It's just because we have a 45-degree angle here. And 45 degrees, sine and the cosine are the same. So then once we do that, if we know our force of friction, and I don't know if it gives us our force of friction in this example. Nope. So if it gives us our force of friction, say the force of friction in this case was 20 newtons. We can solve for the sum the in the x direction, the net force in the x direction, right? Which would be 35.4 minus 20. So we're only going to, at that point, we're only going to use the x and y components to be able to solve for those parts. And then if we knew the y component, we knew how gravity was pulling this thing down, right? We can solve for those as well. And we probably know the normal force, so we'll have to add up all the y components as well to find out the net force in the y direction. Let's see what they do next in this example. All right. So they're just giving you some examples here. We'll actually be going through this more in our class this week, Friday. So if you feel like that's kind of you're getting there, but you want more help, come to live lesson on Friday. We'll be going through that in class. Okay, I think that is the end of this lesson. So if you have any questions on the free body diagrams at all, please give me a holler. I will be happy to help you out. Otherwise, I will see you in the next lesson, which should be second law of motion. Have a great day, everyone.